In the last few lessons, we've spent a good bit of time talking about whole numbers and how to add, subtract, multiply, and divide them. These topics are very important, so I hope that review was helpful to you. I also hope that you have a certain level of mastery of those subjects now as we move forward in this course. Working with whole numbers is a very important thing, but bottom line, life isn't just about whole numbers. We're often dealing with parts of whole numbers, needing to add 2/3 of a cup of water to a recipe, cutting a piece of board 5 3/4 inches long for a small construction project, or giving a small child 1/2 teaspoon of medicine. These are not whole number amounts, but they're what we call fractions. And over the next few lessons, we're going to learn lots of different facts about fractions, what they are, how to tell when two fractions are actually equal to the same amount, how to add, subtract, multiply, and divide two fractions. Now, I know the topic of fractions has been unenjoyable for some of you in the past. Don't worry, we're going to take this step by step, and I'm confident that you can master this very important material. So let's start with just some basic definitions and terminology. First, the word fraction comes from a Latin term which means to break, the same root word from which we get the word fracture in English, like when you break your arm or you break your leg. So the idea behind a fraction is that it represents a part of the whole or a portion of something. Another aspect of fractions is that they are typically numbers which are expressed as a ratio of two whole numbers, like 2/3, which we sometimes call 2/3, or 5/9, 5/9, or 15/4, which we call 15/4. And just a bit more terminology is very important for us. The two numbers which make up a fraction have very special names of their own. The top number is called the numerator, and the bottom number is called the denominator. In a nutshell, they represent two very distinct things. The denominator, which is the bottom number, often tells us how many parts we have broken up the whole into, while the numerator, or top number, tells us how many of those parts we actually have. As an example, we can think of a pizza as being cut into 8 equally sized slices. If we then take 3 pieces of pizza and put them on our plate, then we would say that we have 3/8 of the pizza on our plate. Understanding these different roles of the numerator and denominator will be extremely important, and I'm going to try to talk about numerous real-world examples in this lesson, just to help us fully understand the numerator and the denominator. Now, one of the most important but sometimes most confusing ideas related to fractions is that lots of different looking fractions can actually represent the same quantity. Let's look back at that pizza example I mentioned earlier to see what I'm talking about. Let's say you make a round pizza and you're a bit lazy about how many slices you cut. So you actually just make one big cut right through the middle, leaving yourself 2 large slices, one on top and one on the bottom of the pizza. If you then take one of those 2 slices, then you'll have taken 1/2 of the pizza, right? 1/2 of the pizza is on top and 1/2 of the pizza is on the bottom. Okay, the next day you start from scratch and you make another pizza, a new pizza. This time you're a little less lazy, and so you cut this pizza into 4 equally sized slices. You then take 2 of these 4 slices and put them on your plate so that you have 2 out of the 4 slices of the pizza, or 2/4 of the pizza if we think of it as a fraction. You have 2 out of the 4 possible slices. Remember, that's the role of the numerator, the 2 slices that you have, and the denominator, the 4 total slices. That's where we get the 2 and the 4. The numerator tells me how much I have. The denominator tells me how many total parts there are. But wait a minute, if you just look at the pizza for a moment, you realize that you still have 1/2 of this pizza again, because you've taken 2/4 of the slices. And that means, if you just want to think about the fractions for a second and put the pizza aside, 1/2 equals 2/4. Those two fractions are actually the same quantity. And that's pretty interesting because 1/2 and 2/4 look very different as fractions, but in fact, they're actually equivalent as fractions. And similarly, if you had cut the original pizza into, let's say, 8 equally sized slices, and you kept 4 of them for yourself, then you would again see that you have 1/2 of the pizza. So that means that the fraction 4 divided by 8, which is 4/8, is actually the same as 2/4, and that's exactly the same as 1/2. In fact, we could play this game forever. We could write down infinitely many different looking fractions, all of which mean the exact same thing as the fraction 1/2. We could have written down 3/6, 5/10, or 5/10, and so on. All of them would be equivalent to 1/2. Now, that leads us to an important definition. We're going to say that two fractions are equivalent to each other if they represent the same quantity, even if they look like very different fractions because their numerator or denominator look very different. So, for example, 1/2 is equivalent to 2/4, and 1/2 is equivalent to 4/8, and so on. We're going to use this word equivalent quite a bit in the next few lessons on fractions, so it would be wise for you to put it to memory. Now, this leads us to a few different questions that we really should ask and answer as we walk through this first lesson on fractions. First of all, is there a best way to represent fractions? In other words, is 1/2 better than 4/8 or 2/4? Well, better might not be the right way to say it, but 1/2 definitely has a property that its equivalent counterparts don't have. And that is that 1/2 is written in what we call reduced terms. Now, that phrase, reduced terms, is going to come up over and over again, so let me explain to you what it means, because some of you are probably just not sure what I mean by that. Here's a definition that I want you to keep in mind. A fraction, let's say it's A over B, is written in reduced terms if the only divisor or factor that A and B share is the number 1. So, for example, 4/8, or 4 divided by 8, is not in reduced terms because both the 4 and the 8 share a common factor. In this case, a factor of 2, because 4 is evenly divisible by the 2, and 8 also is evenly divisible by 2. Okay. 2/4 is also not in reduced terms because the 2 and the 4 also have a common factor, again, a 2. And 3/6 is not in reduced terms because the 3 and the 6 both have a common factor of 3. So even though 4/8 and 2/4 and 3/6 are all equivalent to 1/2, it turns out that the only fraction in this family, which is in reduced terms, is the 1/2. Now that makes the 1/2 special in some sense. Better or best, I'm not really sure if that's the right language, but definitely it's the case that 1/2 is special because it's in reduced terms. Let me try to motivate it this way. You might say to me, who cares if a fraction is in reduced terms? Well, let me try to put it to you this way. Which one do you think is easier? Finding 1/2 of a pizza, which only has been cut into 2 huge pieces, one piece on top and one piece on the bottom, so that you've really just cut right through the middle, and all you have to do is pick up one big slice? That's really what 1/2 means. Is that better? Or is it easier to cut a pizza into 100 tiny little slices and then pick up 50 of them? Well, guess what? 50 over 100 is actually equivalent to 1/2. And I'll show you a way to check that in just a minute. But wow, which one would you rather do? I don't want to have to cut a pizza into 100 equally sized slices and then pick up 50 of those little pieces in order to visualize 1/2. It would be the same thing, but it's much easier to just cut the pizza into 2 big slices and pick one of them up. That is an easier representation of 1/2 of the pizza, and that's one of the reasons that 1/2 is a better way of viewing the fraction than 50 over 100. Now, that's not an airtight argument for why fractions which are in reduced terms are the best ones, but believe me, we will most often want to get our fractions into reduced terms when we're finishing our work, and actually in the process of doing some of our adding, subtracting, multiplying, and dividing. We will also want to have our fractions into reduced terms as often as we can. Now, this raises several other questions that we need to think about in this lesson as we deal with our introduction to fractions. For example, how can I tell when 2 fractions are equivalent if the 2 fractions are a bit ugly? I mean, I've been dealing with things like 1/2 and 2/4 and 4/8 in this lesson up to this point. Those are kind of easy to see, but is it easy to tell whether 6 over 14 and 15 over 35 are equivalent? Well, not really at the beginning, but I would like to show you 2 different ways that you can check to see if these 2 fractions are equivalent. So let's talk about that for a few minutes. Let's see 2 different ways to check whether 2 fractions are equivalent. First, you could always take the 2 fractions that you have and just reduce both of them to their lowest terms if you like. It's that simple. If the 2 original fractions are equivalent to one another, then they must be equivalent to the same reduced fraction, or fraction that's in reduced terms. So let's try that in this example. Let's start with the fraction 6 over 14, and let's reduce it down to its equivalent fraction in reduced terms. Okay? That means that we need to start dividing out the common factors, the factors that 6 and 14 share. So, what factor do 6 and 14 both have in common? Well, they're both even, right? So they must both